Okay, 9-8, day 3, the differentiation and integration of power series. Okay, don't write any of this down. Let's just look at it. Okay, so here's the power series we've been looking at. That's what your classwork was on, finding the radius and interval of convergence. Okay, f is differentiable and therefore continuous. So if the function is differentiable, we can find its derivative and antiderivative. Okay, so the derivative is defined as, let's look at the power series. Applying just the simple power rule, exponent comes out front. So exponent times coefficient, and then I subtract 1 from the original exponent. If you look at the individual terms of the series, we can derive those individually as well. Derivative of a constant would be 0. The derivative of the second term, using our power rule, will just leave us with a sub 1. Now check out what happens to the boundaries on the derivative. Okay, so if the power series starts at n is equal to 0, the derivative has to start at n is equal to 1, because we know that the domain of a series is positive values for n. We can't plug 0 into our exponent because it wouldn't give us a power series. Okay, we need our exponents to be positive integers. For the antiderivative, okay, when I apply my rules to the nth term, I add 1 to the exponent, divide by the nu. But then because it's an indefinite integral, make sure that we have our constant of integration there. You can apply the antiderivative rules term by term as well, and that's what's outlined here. Now the importance of this is the radius of convergence of both the derivative and the antiderivative is the same as the original power series. Okay, so R is going to be the same. The interval, however, will differ because we'll have to check the endpoints into different functions. All right, so if we know the radius and the interval, that's very important, and then it's really just an endpoint test into what the derivative or the antiderivative would be. Okay, so that's where we'll start. Let this series be defined as x to the n divided by n. All right, just listed the first 3 terms. So let's start with the interval of convergence for the function itself. Okay, so I use my ratio test. Limit as n approaches infinity. X to the n times x. All divided by n plus 1, that's the absolute value of this, times n over x to the n. Okay, x to the n's cancel. This becomes the absolute value of x times the limit as n approaches infinity. So the absolute value of x is less than 1. So the radius of convergence will be 1 for all of example 1, because we're just studying this one series for right now. Center is at 0, so let's check the interval, the endpoints of -1 and 1. So if x equals -1, I get the series -1 to the n over n. The series converges, so our alternating harmonic. When x is equal to 1, we get the series 1 over n. This is our divergent p-series. So the interval of convergence for f of x, inclusive at -1, and we exclude +1. Okay, part B, find the interval of convergence for the antiderivative of f of x. Okay, so we know the radius is 1. We're testing the endpoints of -1 and 1. So now let's find a series for the antiderivative. So the antiderivative, and I'm writing it out just so you can see it doesn't change. This would be 1 to infinity, add 1 to the exponent, divide by the new exponent. Okay, don't forget the n, which is part of the original series. So now, when I test my endpoints, because we already know the radius is 1, I'll have -1 to the n plus 1, Okay, so when I look at this, this is an alternating series. Okay, and this will converge at -1. All right, limit is 0, terms are decreasing. When I look at x is equal to 1, this gives me 1 over n times n plus 1. And I'm a little bit lazy, not writing all of this in. But when I look at this series, if I compared that to the convergent p series 1 over n squared, so if I do limit comparison, then this series converges as well. And therefore, the interval of convergence would be -1 to 1, inclusive of both. All right, and then lastly, the interval of convergence for the derivative. So now f prime of x will be n times x to the n all over n, okay? And the n's will cancel. So now I just have x to the n. Now notice here, my original series started at 1. My derivative, I don't need to change where my derivative begins because it won't affect the fact that all the terms will be positive. Sorry, bring that down and subtract 1. So this is x to the n minus 1. My apologies. We know that the radius is 1, so testing our endpoints at both -1 and 1, both of those series will diverge. Okay, so the interval of convergence for the derivative is -1 to 1, exclusive. All right, given this function, find the interval of convergence for the function, show that the derivative is equal to the original, show that f of 0 is 1, and then identify a function for f. All right, so interval of convergence, we'll start there. Ratio test. X to the n times x all over n plus 1 factorial. All right, so I know that n plus 1 factorial is n plus 1 times n factorial. They cancel. X to the n cancels as well. Absolute value of x times the limit as n approaches infinity. Absolute value of 1 over n plus 1. So the limit is 0. Therefore, the radius is infinity. And the interval of convergence is the entire real number line. So that'll be the interval of convergence for the derivative and the antiderivative as well. Okay, so let's look at f prime of x. All right, so f prime of x, this would be n times x to the n minus 1 all over n factorial. Okay, now when I check out the boundaries, I do have to change them. Sorry, this should be an n. To n is equal to 1 to infinity. Okay, because I need I need my exponents to be integers, okay, non-negative. So I will change my boundary there, and then let's do a little bit of simplifying. So if I think about n factorial, this would be n times n minus 1 factorial. Okay, I can get these to cancel. And now the series for my derivative n equals 1 to infinity of x to the n minus 1 all over n minus 1 factorial. Okay, so I have to show that this derivative is equal to the original function. All right, well, they look different, so let me start listing a couple terms. So if I list the first few terms of the original, x to the 0 over 0 factorial is 1. When n is equal to 1, I get x. N is equal to 2, x squared over 2 factorial. N is equal to 3. Okay, so now let's list some terms of the derivative. Now, I could, well, let's go back to how the series is defined. So when n is equal to 1, I get x to the 0 over 0 factorial. When n is equal to 2, I get x to the first power over 1 factorial. When n is equal to 3, x squared over 2 factorial. N is equal to 4, I get x cubed over 3 factorial. So I've just shown that they are equivalent to each other. Part C, show that f of 0 is equal to 1. And this may seem like, well, where does this belong? We'll use this technique to find the value of c when we integrate functions. So when I look back at f of 0 and I just replace all of my x's with 1, all of my x's with 0, I notice that everything except the first term is going to cancel. So that's verified there. And then lastly, we've studied this series before. Do you recognize this as a series that you've already studied? So attempt to figure that out for me. And we'll end there for the day.